Get rolling with the lecture. Welcome back. We're going to be talking about Mars today. A lot of Mars concepts, enormous amount of stuff to learn about Mars. But before we do that, we got to check out some photos that some students sent me that are pretty cool looking. So this is the blood moon from last week. And you know what? The blood moon is full moon, right? So now today I noticed when I was driving up to campus that we have a half moon. So it's past. But it's really a cool sequence of photos. And actually, I think this is the reverse of the sequence. In other words, I think this one on the right is that's the first image, and then the last one is up there. Here, so they're pretty lovely. I like this last one. You can see the palm trees kind of casting a shadow against the moon. It's kind of nice. Here's another really lovely one. And the two students that gave me, Sophia and Matt, thank you for that. They're lovely, and I plan to keep using them. So as I always say, keep your eyes on the skies. If you're in astronomy, that's the watchword. Those of you that went to the observatory, what was that, last week? Yeah, for the blood. Yeah, so that was last Wednesday night. We got the observation handouts back, and those are now, the pointage that you earned is now posted inside web courses, so it looks like, right here. Now, we're going to hopefully have a few more observatory sessions, and there's a page linked to the home page where you can actually look at the schedule. I think the next one is February 22nd, so that would be what's today, the 6th? 2 weeks. All right, two Thursdays from now. So hopefully the weather cooperates. And just so you know that, this may have been the only one that goes. It's always the proverbial gamble. And but hopefully we'll get out there and see some stuff. I know a lot of you guys looked at Orion and Pleiades. And did you guys look at Andromeda Galaxy? I can't remember. Yeah. Okay. So, and we're going to be talking about a lot of that stuff. So it's nice that you get out there. Another thing that I want to bring to your attention that I mentioned last night or last week, the exam printouts. Here's like a little image of a exam printout that I've kind of removed some identifying features for. So this is kind of a mock-up. But you may have seen it from other classes. If you have a Scantron type exam, they generate a printout for you on paper that has all the Scantron questions listed and what you answered and whether it was correct or not, and then what the actual answer key was for that question, for each question. And so you can look at that and see what questions you got wrong. Now, the reason that I'm bringing this up is because we will make these available to you instead of on paper as a PDF. All right, and I'm going to make a one-question homework assignment, homework X, tonight, and you can simply answer yes, I would like. That's going to be the correct answer. And homework X is not going to be a regular homework, but I want you to do it to signify that that you want your exam printout. Now, nobody has to take it, but if you do want it, it actually is a nice study tool, because what we'll do is publish, along with that, a little blurb page for each exam form, Form A, B, C, and D. And on that blurb page, you know, like for, say you had Form B, and you got number 11 wrong, you'll be able to look at the blurb page and look at question 11 and get a little blurb about that. You know, so it might be, you know, like Kepler's third law, calculation. Or it might be, you know, definition of quantum fingerprints or something like that. All right, so you'll be able to look at that and the blurb sheet and your printout and kind of use it as a mini study guide for the final, because the final exam is cumulative. All right, so look for homework X, and I'll give you until Thursday to do that. And then if you want, I mean, there's no rush, I mean, because, you know, but we'll get it to you. And actually, Jenny is going to get it to you if you want it. So I'll just do homework X. It's a yes or a no. And it won't go factor into your regular homework and stuff. But I want you to try to just answer one way or the other if you want it. Okay, questions about exams and extra credit and stuff like that? Okay, let's keep going. Last time we talked about Mars, we talked about kind of a little intro to Mars. We talked a little bit about how the surface of Mars is actually not that cold if you're in the right place, the right time of year. We talked about weather. We talked about water and CO2, carbon dioxide a little bit. We're going to talk a little bit more about that. And also about volcanoes and stuff today, and you know, hopefully it will strike your fancy. I want to ask you a clicker question now, so get your clicker activated. If you haven't used it before, I want you to hold the power button down and then press until it flashes, and then type in D, and then D again. That's our frequency. Question. Now this one, hopefully, a few of you answered. No, you don't have. A few people answered D. That's all right. Now, how could an astronomer hunt for water on Mars? How would he do that? Go ahead and read carefully, and then make a vote. Good. In the future, I would like you to start the question when I get to it. Okay. Not before that. You can get it ready, but this way I know how long they've been looking at it. If you do that. So this is kind of hard to see. It's not a disaster, but it is nicer if I know. Sure. Okay, 20 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, this is the basic idea, looking for quantum fingerprints. The spectral lines. Now, I'm going to give you a new vocabulary term concerning quantum fingerprints and the spectrum associated with various compounds, in this case water. And actually, this diagram that's on the slide shows some spectral fingerprints. It doesn't look like it, but that shows some spectral fingerprints for CO2, for carbon dioxide. Right, here's another one. And what this shows you is the reflectance. Okay, so when you're looking at the reason that you see something with color, Daniel, is that the color that you see is it's got to be illuminated by a white light, and then it reflects that color back to your eye in preference to the other colors. Now it might, a red shirt might reflect some red, a lot of red. It might reflect a little bit of blue, green, and the other colors, but mostly what it will reflect is red, and it will tend to absorb those other colors. Right? That's how, something that's red appears red to you, because you're getting the reflection from the illumination to the object and then back to your eye, and what you're seeing is red, if it's a red shirt. If it's a blue shirt, then it's preferentially reflecting blue. Now that's what this vertical scale is, reflectance. So on this scale, up here at the top of the scale, let me get my cursor over here. Here we go. All right. Here's 1 at the top, and here's 0.8, and down here is 0, and 0.2 is here, and then here's another one down here, the second one. So 0.2 means 20% reflected. In other words, it's not reflecting much at that wavelength. And the horizontal scale is wavelength. And these are micrometers. So this is 3,000. This is infrared. All right, 3,000 nanometers, 3 micrometers. And so where this line here dips, it means that it's not reflecting much. You're not getting much of that wavelength. All right, and that is what so let me, outline that one. Then here's another one over here. And these are known as absorption features. In other words, that cloud, this is for a cloud on the surface of Mars, or in the atmosphere of Mars. They're looking at this cloud and they're scanning all the frequencies, in this case infrared, and they're measuring how much light they're getting from it. And it's, and so it's pretty smooth. Everything's just about 1. Here's a little bit of absorption up here, but this is a big absorption feature here. And then here's another one, this dip. It's an absorption feature. Okay, so when we were looking at hydrogen on the first day of lecture, we saw emission features for hydrogen. Pure hydrogen by itself will emit that color of light. But if there's a cloud of hydrogen in front of a thermal source, like the sun or any thermal source, that cloud of hydrogen will absorb those same colors. All right, and that would be an absorption spectrum. And this is what it would look like if you were recording, with a little photometer, in the infrared. You have, most of it up here across the top. Yeah, we're at 100%. Uh-oh, it looks a little dim here. And then, whoa, it's really dim here. And it gets back up to 100% or so. Oh, we got a little bit of dimness. And then here's a big dip right here. And an astronomer can look at that and think, ooh, that's right at the wavelength for CO2 ice. They can even figure out how big the little crystals of CO2 ice are up in the atmosphere. That's what this is doing. So it's kind of cool. And so these absorption lines are another way of using the quantum fingerprints. It's it's like, they're stealing certain colors of light instead of producing certain colors of light. Now, here's just to reinforce. Here's the best diffraction video we have on YouTube is this one, and it's in demonstrations if you ever want to look at it. This is one of my TAs from several years ago, Meg. We did a really nice video on that. It was my first video, in fact. Here's what the emission spectrum looks like. Okay, we saw that. You know, we saw that beautiful red H alpha line, and then here's H beta, kind of an aqua, almost a tealish color, and then some purpley blue ones over here. That's H gamma and H delta. All right. Now those are emission lines. All right. And I want you to, and we've seen that. Right now, if you look at the spectrum of the sun, you know, you look through a prism, or you don't look at the sun through a prism or anything else. I mean, but you let the sunlight shine through a prism, it'll produce a rainbow. All right. The sun produces a continuous spectrum, but if you look at it carefully, this is what you'll see. The sun spectrum actually has bullet holes or absorption features. Every little gap here, like this, here's a big one down here in green. And here's another absorption feature here. And this is spreading out all the colors, you know, really stretching them out and measuring the intensity at every, you know, every subcolor. So going from red up here all the way down to violet down here, you can see there's a lot of absorption features. Okay, this is how it would look. I mean, if you could had a really dark room and you could spread out the spectrum into a really wide, you know, against the wall, you know, like against the wall, the back wall of this room, and then measure the intensity of all the colors, this is what it looked like. So the sun spectrum has bullet holes in it. I don't know. There's a red one up here. I don't know if this is up here is H alpha or not. But there's hydrogen. And so what an astronomer would do is look at these absorption features and say, all right, this one here, and this green one up here, and then this yellow one, and then there's two yellow ones right here. Those are going to correspond to the element sodium. And then they might look at some other bullet holes. Okay, now these, you know, like circle it or put a little star next to it and say, all right, these ones correspond to aluminum or carbon or some other element. And some stars, you know, we look at stars, this is what we see. You know, we see this. And what this is telling us is that in the atmosphere of the sun, you know, the photosphere, the hot part, the surface of the sun, is putting out a continuous spectrum, but in the atmosphere above that, where the light is produced, there's hydrogen, there's carbon, there's all these other other elements up there in gaseous form, and they're absorbing these colors, right? And so a scientist, an astronomer would look at this, or somebody in a CSI lab, you know, it's the same kind of thing that they do, except, you know, they're not looking at the sun. They're looking at some chemical, and they're looking at all the bullet holes. Will tell them, all right, I've got some hydrogen, I've got some sodium, and I've got a lot of carbon, you know, or whoa, I got a lot of hydrogen. All right, and I know you got a question. I'll get to you in a second. And one thing I want you to make a note of in this is that looking at these spectral lines, these absorption features, these absorption lines, scientists in the 1800s found some spectral lines that they didn't know what they were. You know, they saw hydrogen, good. They saw carbon, good. They saw sodium, good. They saw a bunch of stuff. But there were some spectral lines they couldn't check off the list. And you know what that was? They named it an element, helium. And that's how we discovered the element helium. That's why it's called helium, because it was discovered in the sun. Now we know, now we've gone and looked for it, we find it in natural gas, you know, that comes up out of the ground, you know, by oil wells and stuff like that. And it's a normal part of natural gas. So we have helium on Earth, but we didn't even know it because it's lighter than air, and it'll, you know, like the helium balloons you get at the store, or for your birthday party at Chuck E. Cheese or wherever you go for your birthday party. You know, those little helium balloons, that's, you know, that's what we got. So those are absorption features. Now that's going to be important for us because we're going to be talking about Mars. Let's get back to Mars. And in fact, let's talk about volcanic activity. Now this is an overhead view of the largest volcano in the solar system. It's the largest volcano on Mars. It's the largest volcano anywhere. It's called Olympus Mons, Mount Olympus. And you can see that they've superimposed the outline of the state of Arizona inch for inch, meter for meter, kilometer for kilometer, mile for mile. And yeah, Olympus Mons is basically the size of Arizona. It's pretty ginormous. And you can see it here. And there's no trees and stuff. You know, like if you're in Arizona, it's a lot of desert and stuff, but up in the mountains, there's trees and stuff. Not on Olympus Mons. We don't see anything on the surface of Mars that, you know, we don't see any vegetation. Okay? So this is like looking at a real deserty volcano. So you're looking at rock in that picture. All right. Now, this particular type of volcano is very similar to the volcanoes in the island of Hawaii. So what I'm saying is they're a little bit different. This kind of volcano is different from like Mount Vesuvius in Italy, over by Naples, or you know, Mount St. Helens out in the Pacific Northwest. Or, you know, they got that big one, I can't remember the name of it, down in Mexico City. Down in Mexico, they got a few volcanoes. Down in Central America, they got some big ones. Those are a little different. Yeah. How are they different? They're different because the volcanoes in Hawaii, in Mexico, the volcanoes in Japan, Mount Fuji, that's a volcano. The volcanoes in Alaska, the volcanoes in the Pacific Northwest. They're at the margins of continents. And where a continental plate rides up over or dips down under the oceanic plate is heavier, it's mostly basalt, and it's moving. And the continents are drifting on it. And where the continents, or where two continents collide, like here's another place where continents collide, is the Himalayas. And let's see, what was I? But the Himalayas are not famous for volcanoes. But that's a place where mountains have formed because you know, the subcontinent of India has smashed in, you know, moving north over millions of years, has smashed into the Eurasian continental plate, formed mountains. Philippine Islands, all around the Pacific, it's called the Ring of Fire. All the continental plates are colliding with various pieces of the Pacific, the oceanic plates. And where those collisions happen, you have volcanoes, but Hawaii is out in the middle of the ocean. There's no continent there. Hawaii is sitting on top of a hot spot in the earth. We don't know why it's there. But we know that at that spot, and there's a couple others in the earth that we know of, Hawaii is sitting on a hot spot, and those volcanoes are completely, they work differently. All right? They don't have as much water dissolved in the lava, and you know, various things, the various features, they're shaped differently.
Not as explosive.
They're right, just because there's not as much water. They're not as, you're an expert on all this.
Yeah, they're not as explosive. They tend to just kind of like ooze out lava rather than having like the big eruptions that throw
Yeah, like
gas
Mount
and
Vesuvius,
ash
which
everywhere.
kills people and stuff. Hawaii, I mean, you can still get greased up there, but
Yeah,
you know, if you step wrong. But But those they're called shield volcanoes in Hawaii. Okay, and they form this. And you know, the biggest mountain on Earth is Hawaii. If you go from the bottom of the sea, where it starts, to the top of Mauna Kea, I think, it's actually bigger than Mount Everest. All right. So, but it starts under the ocean. So SpongeBob would think that that's the biggest planet on Earth. And so, okay, now that brings it back home. But anyway, so you know, here's another place where there's a hot spot, and it's a little different from Hawaii, but it's sitting on a thermal plume working its way up from the core of the Earth. Yellowstone, the Yellowstone supervolcano, and all those geysers, and Yellowstone is a big volcano that's blown so catastrophically, you know, the entire top of the volcano is gone. And Yellowstone National Park is sitting in the crater left over from that big mega eruption. You know, I don't know, I can't remember how many years ago, but I think it's on the order of 100,000 years ago when they think the last eruption of Yellowstone was. And it greased animals all over North America, you know, huge, buried under volcanic ash and stuff, you know, worse than any nuclear war that we could ever think about, you know, and that's just one mega volcano in Yellowstone. But that's another place where there's a hot spot. You know, it's just a little place on Earth, in the interior of the Earth, that sends up a little, you know, spot of heat, and it causes Yellowstone, it causes Hawaii. Another place is the middle of India, the Deccan Plateau in India is a hot spot, and that's where the volcanic activity is in India. And it's not volcanic; it's more like it's not explosive like Mount Vesuvius. It's it's these big plateaus of, you know, lava flows that go for many, many miles and stuff like that. Anyway, so Olympus Mons is similar to the Hawaiian volcanoes. All right, check out the height of it, 26 kilometers. Ooh. So let's see, a kilometer is about 0.6. So 26 times 0.6, see, that'd be 12. That'd be that's over 15 miles. Close to 16 miles in height. So that's like 2.5 Mount Everests from bottom to top. So it's ginormous. It will cover up the state of Arizona. Now, here's the thing about it. We haven't seen it erupt. Now, we've seen other volcanoes on various moons over or orbiting around Saturn and Jupiter that have erupted. We can see them, you know, shooting geysers into space and erupting stuff. We haven't seen this one blow. You know, so maybe tomorrow night. You know what? That'd be pretty cool. You know, if this thing ever blew, they would train every single telescope on the planet to record everything that they could possibly get. X-ray telescopes, infrared telescopes, radio telescopes, optical telescopes, ultraviolet, the kitchen sink telescope. And amateurs as well. If this thing is going to blow, because you know what they'd look for? Quantum fingerprints. They'd be looking for how much CO2, how much water's coming out, how much pyroxene is blazing out of there. They'd pick that up as well. Oh my goodness. But nothing yet. All right, here's the state of Arizona. Let's take a look at this. All right, now Olympus Mons is basically the size of Arizona, right? And here's Hawaii. And you might think to yourself, oh yeah, Hawaii's pretty big too. It's about the size of Arizona. Yeah, except it's the islands of Hawaii that have the volcanoes. And look, here's the island, the big island, Hawaii. That's way smaller. That island is way smaller than Arizona, and therefore way smaller than Olympus Mons on Mars. And on that island, there's more than one volcano. There's like 4 of them. Three of them are still active. All right. One of them that's dormant, we got some really super telescopes up on top. We got some observatories up there. So to us, Mount Vesuvius, Krakatoa, all these volcanoes that we've observed erupting and stuff, they're pretty disastrous. But oh my goodness, Olympus Mons, you do not want to be around when that baby blows, because maybe that's why there's no life on Mars, because of Olympus Mons. All right, let's do another question, vocabulary term here. What do you call this molten lava stuff? You remember what that?
I actually had a homework problem in my geophysics class to calculate the grade of Olympus Mons, and it's like you wouldn't even notice that you're on the mountain.
Seriously, it's so big, yeah.
Well, it's so big, but like in size, but compared to the height.
But it has some escarpments though as well, doesn't it? So
yeah.
I mean, you would see those. But
but
other than that,
it's pretty much flat.
yeah, that's interesting. Yeah, I tell you what, that's a.
I actually calculated too during Hurricane Irma that the size of Hurricane Irma was actually like almost bigger than Olympus Mons in the area.
Why did you do that?
I was bored. I'm a physicist.
Face palm. I don't know.
Not much to do when there's no electricity.
All right, good. 5 seconds to vote. 5, 4, 3, 2, 1. Oh Lord, we got to do something about that. All right, you guys got it right. Magma. Most of you got that one right. Yeah, magma. And we're actually going to be talking about magma and lava and stuff here. Now, you might. And now we're dipping over to other questions, but actually, this is also related to volcanoes, because how do you think there's any atmosphere on our planet or Mars? Yeah, volcanoes. Every volcano that erupts on Earth puts out, huge amounts of CO2, depending on which volcano it is. And, more than, all the human production of CO2 for like 80 years or something they could put out in a couple days of eruption. So it's, now, the thing about the atmosphere of Mars is it's pretty distinctive. It's mostly CO2. So if we were on Mars, near the equator in the summer, it might be fairly warm. You wouldn't need to, have a total spacesuit, because it might be a little bit chillier than it was this morning. I think it was 50, might be 40 degrees Fahrenheit. But definitely you'd need breathing apparatus, some scuba tanks, because, there's not much oxygen. There's some nitrogen, trace amount of water vapor. So we can, how do we find that? Absorption features, and any of the gases that we can pick up, or even crystals, like the cirrus clouds that you see up overhead on, certain days of the year, those are so high, those aren't droplets of water, those are actually ice crystals, they're up that high. Now the fluffy white clouds that you see closer to the ground, like a thunderstorm, those are actually micro droplets of liquid water. But so we see all kinds of stuff in the atmosphere up there on Mars. We got about 900, well, not 900, but we got a bunch of spacecraft orbiting. We've had spacecraft fly by. We got a bunch of them sitting down there, walking around. We've had all kinds of stuff on Mars. And this guy, that brings to mind, this afternoon, approximately 1:30, there's going to be that Falcon 9 Heavy launch. 1:30, the launch window starts at 1:30 and it goes for a few hours. And who knows if it's going to actually launch, but hopefully it'll go. And if you are out and about, if you're on campus, it would be worth your while. Go to the Memory Mall over here, and where the tailgating is and stuff.
Go to the top of parking garage.
Oh yeah, top level of parking garage probably be pretty good too. You should be able to see it if it launches. And I've seen night launches, but I've never seen a daytime launch because I'm always busy, giving exams and staying one step ahead of the students. But I might actually try to slip out and see that Falcon. And I know a bunch of your classmates had seats. There's a lot of empty seats in here today. Dr. B, I got a bunch of messages from students over the weekend and stuff and last week. Dr. B, I'm not going to be in class on Tuesday because astronomy related. I'm going to go watch the Falcon 9 Heavy launch over in Titusville or wherever they're going. But Dr. B, it's I can be excused, right? Because it's astronomy related, right? And to tell you the truth, it is astronomy related. And I would like to go to Titusville right now instead of being here. But anyways, but if you can go out there and look at it, it'll be good. And supposedly they're going to send that. Why did he put a red sports car, a red Ferrari?
Yeah, he needed to send something that was somewhat representative of a payload mass, and he has a lot of Teslas.
Yeah, it's a Tesla. It's not a Ferrari. It's a Tesla.
Advertising.
Yeah, but I just was wondering why they didn't. Oh, that's right. He owns the Tesla company. Right. Okay.
That's cheaper than.
Yeah, so it's a little interplanetary advertising campaign. I was just wondering why he didn't launch some kind of a spacecraft. Anyway, so hopefully, supposedly he's going to send that on a trajectory towards Mars, and a Tesla crash landing on Mars. That would be fun. All right, now we mentioned this last time. We've had abundant probes from orbit, from flyby, and then these rovers and landers. So we know there's a lot of liquid. There's a lot of water. We know that liquid water was once abundant on the surface because we could see canyons that were formed by flowing enormous amounts of flowing water. There are also, occasionally we see meltwater form little rivulets and gullies. I don't think they've ever caught it and snapped a photo of the water, but they can see it, the remains of it on hillsides and stuff on Mars, like a spill. You spill something, you don't see the spill, but you can see that somebody has spilled something, and that's what it's like. They have also found minerals and rocks that form in water. And it's, I'm not really up on that, but I do know that the presence of water changes chemical reactions, also pressure, water pressure. If you're under the ocean, it can change the chemical reactions and make an igneous rock look bluish green, for instance. I know that. And so they can identify minerals that form underwater. So they know that in various places there have been abundant water. But right now we don't see any lakes or rivers or anything like that. There's also lots of H2O in the polar ice caps. Now, most of the polar ice caps are carbon dioxide, CO2, but a lot of water up there too. Mostly CO2, but plenty of water. It's not shy of water. All right. Now, the reason we're looking at the concept of the atmosphere is because we want to understand volcanoes and other things. And one more thing that we need to know is the solar energy budget. Okay? And this is basically the amount of energy that strikes the outer atmosphere of a planet per square meter per second. So it's watts per square meter. Right now on Earth, the solar energy budget, or what we call the solar constant, is 1,367 watts per square meter. Now that's the average. It's not really a constant of nature because the sun has weather. And so the solar constant can go up and down a few watts per square meter. So what that tells you, you can make a note of it, 1,367 watts. That would be enough power to operate like a hairdryer. Not a big hairdryer, but a small one. Okay? Or maybe a microwave oven. All right? So if you had 1 square meter of photoelectric cells orbiting, and your photoelectric cells were 100% efficient, they'd get 1,367 watts of power from that, 1 square meter of photocell. So my desk up here, my lectern, is about 2 square meters, when you're looking at it. The front surface is about 2 square meters. So this thing here, up here, if we had a solar cell, 100% efficient, about the size of the front of this lectern, we'd be catching about 2,700 watts. I mean, if it was up in space. Now, it wouldn't be true down here at the surface, especially here at sea level, because we got a lot of atmosphere, so the sunlight gets, a little bit distracted. But up above most of the atmosphere, a couple 300 miles and higher, yeah, about 1,367. Now, Mars, it doesn't get as much because the sunlight's dimmer out there. It's spread out. And it works out to about 591 watts per square meter for every square meter of your solar cell that's facing towards the sun. All right, so that's a fair amount of energy, 591 watts. All right, and these spacecraft, they design the spacecraft that's orbiting Mars or orbiting Jupiter or Saturn or whatever planet. They engineer it to have enough solar cells to get enough of this energy to radio back to Earth. Radio all their data through the radio frequencies back to Earth. So they got to work all that stuff out. Now, here's what a planet does with the solar radiation, the radiant energy that arrives at the top of the atmosphere. Some of it gets reflected. Here on Earth, we got clouds. The ocean reflects sunlight. Okay, so that'll have a cooling effect. In other words, the planet's a little bit cooler for every watt of energy per second that gets reflected. It doesn't heat something up. But if it gets absorbed, like by your skin or by a rock or by water, water will reflect and absorb, then it'll heat it up. All right, and that is why the climate of Earth is basically controlled by the oceans of Earth, because the water, most of the surface of Earth is covered by oceans, and a lot of that is liquid water, except for up at the North Pole. But most of it is liquid water, and liquid water absorbs enormous amounts of energy to raise it by 1 degree. Right? It takes a lot of energy. Water is one of the, so heating up metal, and you've done that. You put a piece of metal out at the beach, and you pick it up, you're going to burn your hand. But you go in the water's just nice and warm, or maybe even cool. This time of year it'd be cool. All right, so absorbing, reflecting, and here's another thing that the atmosphere does. It will scatter the light. And that's why Earth's atmosphere, our sky looks blue, because the sunlight scatters blue light in a different way, or the atmosphere scatters light a little bit differently for blue than for the other colors, and for that reason the sky looks blue. All right, so that's not absorbing or cooling. Excuse me, it's not heating or cooling, but it is a transport mechanism. All right. Now, here's some more specs for Mars versus Earth. All right. And in terms of mass, you can go back later and write these numbers down from YouTube. But the mass ratio, definitely write down the ratio. Go ahead and make 4 columns. And so the middle 2 columns, 1 for Mars, 1 for Earth. And then the ratio column, 1 to 9.3. So Earth has about 9.3 times the mass of Mars. It's a lot bigger, right? The radius is about 1 to 1.88. So Earth's radius is about 1.88 times bigger. Do you still have a question? Okay. All right. I forgot. Sorry. The acceleration due to gravity at the surface gravity, g, little g. On Earth, good old 9.8 meters per second squared. 9.8 meters per second of downward speed for every second free fall. But on Mars, way pokier, 3.71. And on the surface of the moon, it's like 1.6 something meters per second squared. So that's why, you know, when you look at the movies of the Apollo astronauts, a lot of times they're jumping, they make these great leaps and skipping and jumping across the surface of the moon because gravity is so much weaker up there. And Mars would be weaker too. So you could probably, if you can't jam on Earth, you might be able to jam on Mars. So space jam on Mars, you could be like Michael Jordan, be like Mike. The orbital size, 1 astronomical unit for Earth, 1.524 for Mars. So it's about 52% further out. That's this ratio over here. 1.524 astronomical units for Mars and 1 astronomical unit by definition for Earth. All right, now here's the solar constant. And this is what I was talking about. 591 watts per square meter. All right, not quite enough for a hairdryer. Maybe for a hairdryer for a mouse. 1367 for Earth. Watts per square meter. Yeah, that's enough for a hairdryer on Earth. And the ratio is 0.43 to 1. So Mars gets about 43% of the energy per second, square meter for square meter, that Earth does. Okay. And that means that it's basically the weather on Mars is a little bit cooler. They don't have any burning hot days on Mars. Now, if you go back into the inner solar system and back up to Venus, Venus is totally HOT. It's completely hostile atmosphere on Venus, but Mars is a little bit cooler. Now, here's a picture to help you understand the solar constant, which is sometimes denoted by the symbol capital C. All right. Now, here's a picture of Earth right here. And in perspective, this kind of red circle is supposed to represent Mars. So I'm drawing a disk now, the same size as Earth, but it's a disk, it's not a sphere, and it's facing toward the sun. And here's a disk, same size as Mars, and it's facing toward the sun. So here comes some sunlight. And this disk, for every square meter of this disk facing the sun, you get 1,367 watts per square meter. Now here's an interesting calculation. How many square meters is on that disk? It turns out to be a huge number. And so the amount of energy coming from the SUN to our planet is enormous. You know, the amount of solar energy falling on, for instance, the campus of UCF, you're talking about the per second, it's like in the order of magnitude of a nuclear weapon. That's how much energy that we get per second from the sun on something like the size of a city, like, and UCF is like a small city, right? I once did the calculation for the city of Ocala, and it's amazing how much energy the city of Ocala, and that's just a little patch of ground up in the middle of Florida. And all the different pieces of ground there are in the United States and around the world, enormous amounts of energy coming from the sun, way more than we produce, even with our biggest nuclear weapons. Okay, so here's the sun. Now, this sun breezes past the Earth, but it heads out to Mars. Here it is. And it's out there, it's diluted down. It's the same sunlight, same colors, same absorption lines, same absorption features, but there's less of it per square meter. And so for that reason, there's less wattage per square meter. All right? Now, all this is important. The atmospheric composition, the solar constant for Mars, because of the next few slides. Key quotation from chapter 10.4. Talking about Mars, and we have meteorites that have fallen to Earth that get blown off the surface of Mars. And most of them are from volcanic basalt formations. Now, basalt, B-A-S-A-L-T, is a dark, usually kind of a dark gray rock. It's an igneous rock. And the floor of the oceans are mostly basalt. Well, underneath all the mud and stuff like that, the coral and stuff. But, the bedrock of the oceans is mostly basalt. Did you ever see those beaches in Hawaii that have black sand? Basalt. All right. So most of the Martian meteor, but we pick up a piece of rock, like Jenny was saying the other day. If you're walking around Florida and you find a dark rock and you're out in the middle of the woods or someplace, not by where they're tearing up a road, so you might, if you're tearing up the road, it might be a piece of asphalt or something. But if you're out in the woods and you see a dark rock, it's a good chance it's a meteorite. But how do they know it's from Mars? Like this one. This is the picture that goes with that quotation. This is an actual Martian meteorite. The reason that they know it is because we know the atmosphere of Mars. We've had enough landers, orbiters, and rovers and flybys that we know the composition. What did I say? 96% CO2, 3% nitrogen, a little bit of water. They've analyzed the atmosphere of Mars to a T. So we know what's in there. And guess what they find in these meteorites? They find little teeny bubbles of the Martian atmosphere. Fossilized, I guess you could call it fossilized, blasted into the volcanic rock. When it cools, little teeny bubbles of the atmosphere are in there. You're just kind of like, when you make a smoothie at home, basically you're grinding stuff up and you're adding a lot of air to it. All right? That's why it expands in volume. Right? So that all that air, if you're doing it on Mars, it would be Martian atmosphere. All right? Now, if that smoothie solidified, was ejected into space and landed on another planet, they'd say, this smoothie meteorite has got the atmosphere of Earth or whatever planet that you're from. So now, what are we looking at here? What does that look like? Sherbet. What? No. That's It's on Mars. It's called Tharsis Tholus. Go ahead and write that down. Gosh. Everybody's a wiseacre. Now, Tharsis is, we're going to be looking at this picture about 70 times here the rest of the next 15 minutes. Tharsis it actually gives the name to half of Mars. All right, so here's what they call the Tharsis hemisphere of Mars. And this is kind of like a topographical map. This big white pimple over here, this one right here, right there, that's Olympus Mons, I believe, if I recall correctly. This gash here, this kind of greenish gash, and you can kind of see it curves around over here. That's the Valley Marineris. That's a big canyon formed, we think, by flowing water. Now, the other hemisphere of Mars is called the Hellas hemisphere. And here's, you can see it's got a basin here, right here, and topography up here, and then this is low. So if there ever were oceans on Mars, they would look something like this. All right, and let's see, this little thing here, right there, where the black arrow's pointing to, yeah, that's the summit of Tharsis Tholus. Now, to compare that, let's compare it to some terrestrial volcanoes, right? Look at that. That's a volcano in Iceland. Wait a minute, let's go back here. All right, so there's Iceland. Here's Sudan. Look at that, a volcano in Sudan. Sudan is supposed to be like total desert, right? But not here. It's got a lot. See that, all that water in the crater of that volcano? Here's one in the USA. All right, it's got an observatory up at the top. And it looks like there's not much water up there. Siberia. So the volcanoes of Earth look a lot like the volcanoes on Mars. Make a note of that. You know, we're looking at these structures on Mars, and they look like Earth volcanoes, and that's why we know that they are volcanoes. They're pushing out the atmosphere of Mars. They're making igneous rocks. Some of those igneous rocks are ejected as meteorites that eventually land on Earth, and people collect them and find them, and then they analyze them. And it's just, you know, there's a lot of interesting things about Mars. So let's just keep going here. Here's a close-up. Here's the other hemisphere. Now up here on the Hellas hemisphere, I want to draw your attention to this little spit of land. It looks like, I mean, if this was the Earth, we would think, okay, it's a little peninsula into the ocean. All right, so right up there, nothing much cooking up there. You know, there's no volcanoes. You know, it's not a big, but you know, like you can maybe see, I don't know, you can't see any volcanoes. You see a lot of craters, though. You can see all those craters, the impact craters. Yeah, there's no weather. There's no more running water on Mars, so those craters have been there for billions of years. All right, and people study that, as Jenny said the other day, and they get a good estimate of the age of, you know, whatever surface that they're looking at. Now this one up here, go ahead and write this word down. This may become a very famous place. Nili Fosse. Now the moon astronauts, the Apollo astronauts, they were sent to the moon to scout out various locations and basically bring back geological samples and the soil of the moon, to be analyzed. What kind of stuff. And people knew there wasn't any life, there wasn't any atmosphere on the moon, there wasn't any life on the moon, so they weren't looking for life. That we are in a lot of other places. But on the moon, they had a set of targets set by geologists. Let's go to the Lunar Highlands. Let's go to the Fra Mauro Formation. Let's go to the Sea of Tranquility Base. The Eagle has landed. You've all heard that. Those are geological targets. This is possibly a biological target. So write that down. Nili Fosse, biological target. And why is that? Because, as you can see in this slide, generated by M.J. Muma et al. Back in 2009, they found methane. Specifically, they found plumes of methane gas. How did they know it was methane gas? Quantum fingerprints, absorption lines or emission lines, one or the other. And it was seasonal. In other words, it wasn't a constant source. It was a source that came and went, depending on the season. All right? Now, my backyard, we have a papaya tree. And that papaya tree, is everything okay back there? All right. My papaya tree got greased by the cold wave a few weeks ago. It looks dead. Of course, you can't kill a papaya tree because it's coming back down at the base of it. But the big tall shoots, they're all brown and withered and stuff. Our mango tree got blazed, all right, because of the weather, the season, cold season. So these guys, they were analyzing data from one of the orbiters. And they found that there was a plume, a seasonal plume in the atmosphere of methane. Now, why is methane important? Well, let me just tell you, on our planet, there are biological sources of methane. And some really big biological sources of methane are the south end of a northbound cow. All right? It's just a naturally occurring gas from the digestive system, the intestines of a lot, basically of vegetarian type creatures like cattle and stuff like that. They produce a lot of methane. All right. Now I'm not going to say anything further than that, but and that's seasonal. The cattle can move from point A to point B, and if it was trees, here in Florida, trees, they turn, they lose their leaves. If you're a little further north, they turn colors, and with the seasons and all that stuff. Now that's not methane, but it's something seasonal that's observable on a seasonal basis, and that's what these guys found. So they're not sure. They're not sure, but they're thinking about it. Everybody's thinking about this. All right, this plume that they found, is it spurious? Did they really see it? And we think they did. There really is a plume of methane that comes and goes on a seasonal basis up there at Nili Fosse. So, if you, you're awake, good. If you get to go to Mars one day, instead of snoozing in my class, you become an astronaut and you're in the first mission to Mars, this is where you might go. And you're not going to be on a geological expedition, you're going to be on a biological expedition. Now, it's highly unlikely that they have little green men up there, but they might have some kind of a lichen or bacteria or something like that. And it may actually be under the surface. We don't know. But we have our eyes open. Question?
I just want to say at least you can sleep on the ride there.
That's right. So keep awake now, and then you get on that rocket ship, you have a lot of time to snooze and other stuff. Check your Netflix, etc. Now, one more thing. This is not the best. This is not the most interesting. This is the most interesting. ALH 84001. This is a meteorite. It fell in the Allen Hills ice field of Antarctica and was found back in 1984. Let me spell that for you. Allen, A-L-A-N, Hills, H-I-L-L-S, ice field, I-C-E-F-I-E-L-D. In other words, one of the big ice fields, glacier areas of Antarctica. And apparently, Antarctica is a nifty place to find them because, you know, ice is usually kind of whitish. And so if you find something dark on the surface, like a meteorite, you know, it's right there. It's easy to see. Now this one they picked up, and they took a. You can't really see it in this image, ALH 84001, but they took a slice of it and analyzed it and put it under an electron microscope. You know, they looked at the minerals. You can see the magnesium, iron, orthopyroxenes. They found little bubbles of glass, little pieces of glass, what they call impact glass. And in that glass, they found little bubbles. And I remember when they were first studying this, when I was teaching up in Vermont, we went to a colloquium with this really famous astronomer, and she was talking about this, and one of my students was a geology major, and she and I were sitting together, and a bunch of my students were sitting there, extra credit to go to this colloquium, and she said, Dr. B, how do they know it's from Mars? I said, I don't know, why don't you ask her? And by God, she asked her. She got up the nerves, and her name is Jill Tarter. And she's the one, if you've ever seen that movie Contact, she's the woman that is the real life person upon which that movie is based. You know, the Jodie Foster character in Contact. And so she's pretty famous. My student Erica, you know, she raised her hand. How do you know it's from Mars? And she told her what I just told you. That in those little teeny bubbles in the glass, in the impact glass, in this meteorite, they found little teeny bubbles of Martian atmosphere. And why do they know that? Because they knew it's 96% CO2 and 3% nitrogen and a bunch of other traces. They knew it. Signature. It had to be from Mars. But here's the best part. When they took a little slice of it and they looked at it in a microscope, they found what they think is a fossil of a life form. And you know what it looks like? It looks like a worm, but it's really small. It looks like a worm that you might see, you know, in a coral formation. You know, a segmented worm that you see under the sea. Oh my goodness. Mars. Lots of interesting. So, okay, so, you know, if you get in the second mission, they might go looking for where this rock was. All right? Or if you return. And catch up your sleep and then go back another time. You know. All right, let's dismiss. Keep reading about the terrestrial planets. We'll be talking about Venus and Mercury on Thursday. You're dismissed.